everyone. So my plan for today is to follow up on what we did in the last class as well as to do a brief recap. So what I wanted to do is to make you realize that electrons in semiconductors are nothing but quantum mechanical objects, and to appreciate the fact here that quantum mechanics governs all. Now, from such a perspective, I would like to really give a historical background as to why in the first place we really needed to model these electrons in semiconductors as quantum mechanical objects and lay down the foundation of solid state physics, which you will really see in the later part of this course provides us deep insights into the realm of quantum mechanics. Now, starting from what we did in the previous class, where we actually derived the Drude model, to explain the conductivity in metals. Now, again, so giving you a historical insight, as I think I have really passed on this handout here, and I think you'll probably read it up, since the assignment that's coming up will probably need you to read this up and do a critique of this paper. So anyways, so coming back to the discussion where we are explaining what happened in the early 18th century, people knew a lot about metals, but they really didn't know a lot about semiconductors. So speaking of metals, what people in those days did was they measured the electrical conductivity they measured the thermal conductivity, and finally they also measured the optical conductivity. So I'm going to talk about the optical conductivity a bit later in the course, as you'll probably have some assignments based on this. So in the 1850s, people tried to measure these properties for various different metals that was available at that time, and Drude came up with his model, which explained that electrical current is nothing but the electrical conductivity times the electric field. Now we have really seen this in the last class, that again electrical conductivity can be written as the electron density per unit volume times the charge of each electron squared times tau. So tau is basically the scattering time, or the distance an electron travels between two scattering events, divided by the mass of each electron. So at that time, back in the 1800s, this was a theoretical construct, since people never really knew what was the exact value of a charge of an electron or the mass of an electron in any of these materials. But later on, towards 1890s, when people knew the value of these quantities, that Drude was finally able to give very plausible explanation of how electric current is generated in metals, or for that instance even in semiconductors. But speaking of this, Drude was not really famous for the model that he had proposed, but he was really famous for something else, and this, as I would say, has been an interesting observation which has baffled a lot of people for more than half a century. So what he said was, if you